Welcome to Programming Sockets in Python. My name is Christopher, and I will be your guide. This course is about socket programming. A socket is what you use to interact with networks from your code. The Python socket module is a low-level library that is a thin wrapper for the underlying C code. That means it isn't your friendliest neighborhood, and you have to write code to manage more things than your typical Python program. But this course will show you the ropes. In this course, you'll write a couple of servers that listen to sockets and manage connections, as well as write several clients to talk to those same servers. At the base socket level, you'll be slinging bytes. That gets tiring after a while, so you'll probably want a higher level abstraction. That's where application protocols come in. You'll learn how to consume those raw bytes and turn them into useful Python content. The code in this course was tested with Python 3.13. The socket library has been around forever, so pretty much any Python 3 should work. I also use several network tools along the way, which if you want to duplicate everything I'm doing, you'll have to install. I'll point them out as I go along. One of the challenges when writing an intermediate or advanced course is knowing your audience. For a beginner course, you have to start at the beginning. This course isn't that. Since I'm not sure how much networking knowledge you have, I've provided some background. If you're comfortable with network stuff already, you might want to skip forwards. If you're already familiar with IP addresses, ports, network interfaces, and understand how a protocol like HTTP sits on top of TCP/IP, and all you want is to see sockets in Python, you could skip to the Using Sockets section, the first lesson of which is titled Listening on a Socket. If you're okay with IP addresses and ports, but could do with a refresher on what a packet looks like, then maybe skip forward to Seeing TCP/IP. Otherwise, I'd suggest just continuing from this lesson on to the next one. Speaking of the next one, next up, what happens on the network when you fetch a web page? In the previous lesson, I gave an overview of the course. In this lesson, I'll introduce you to networking concepts used when writing sockets. If you're like me, you use the web every day. Let's be honest, almost every waking hour of every day. There's a chance I do it in my sleep as well. Just what does it mean to use the web, though? Well, your computer establishes a connection to another computer, say python.org, and asks for a web page. And then python.org obliges and sends back text that your browser renders. I've glossed over a few things here, so let's drill down one layer. First off, computers don't use names, they use numbers. So when I say python.org, what is actually happening is my computer is connecting to another computer that keeps a master list of all the domain names and maps them to numeric addresses. Even this is an oversimplification, but let's stick with it for now. The numeric address for python.org is 151.101.0.223. That's also an oversimplification as they've got multiple addresses, but let's stick with this for now. Yeah, I'm going to be saying that a lot. The good folks at python.org are probably offering all sorts of computing services. They definitely host web pages, and I suspect they also support email and other things. To distinguish between these services, a server has another number called the port. Each service is registered against a port number. A lot of services on the internet have standardized port numbers. For example, the web is port 80, while the encrypted web is port 443. So to connect to python.org, I'm actually connecting to 151.101.0.223, port 443. Establishing the connection to that port on their machine is only the first step, though. Since I want the connection to be encrypted, a bunch of data goes back and forth between my browser and the server that does all the fancy math that makes sure the conversation remains private. This is done over a protocol known as TLS. Once the TLS connection has been established, I can finally ask for the web page. I do that with yet another protocol, this one being HTTP. Yes, there are protocols on top of protocols here. It's kind of like the turtles, it's protocols all the way down. The HTTP protocol allows me to say things like, hey, don't compress the stuff I'm asking for, and hey, this is the page I want. With all that done, python.org's web server finally responds with the content that I requested. Let's start peeling apart some of those protocols. When I make a connection to an address, I do so using a socket. A socket is an abstraction provided by your operating system which connects two applications. The applications can be on the same machine or on different ones. You can send and receive data over a socket as a stream. This is similar to reading and writing data to and from a file, but the data in this case is sent and received by whoever is on the other end of the socket. You know those protocols I was talking about? Well, there are protocols below them, and thankfully your operating system provides an interface for creating sockets that abstracts away even the lower level stuff. In Python, you take advantage of the OS's mechanism through the socket module. Let's move from the vague, there are protocols below your protocols, to the slightly more specific. You can think of your network as a series of layers. At the bottom is Ethernet, which is the hardware and what is known as the data link layer. This is your actual network card along with device drivers your operating system uses to interface with it. Ethernet isn't the only networking hardware out there. There are others, but as most of the internet is based upon it, it's the one you're most likely to bump into. Being an old man, I could regale you with the stories about the pain in the butt it was when you had to interconnect offices that used different hardware, but I'll spare you. Sitting on top of the data link layer is the Internet Protocol Suite. Yep, that's where the internet gets its name from. This suite is split up into layers as well. The bottom portion of the internet is the IP layer, also known as the Internet Protocol. This layer is responsible for sending and receiving the chunks of data known as packets over the data link layer. This layer is fairly simple, and if something goes wrong during the transmission or the packet gets mangled, this layer does nothing about it. It's just there to send data between two machines. On top of the IP layer, you have a choice. The first option is UDP, which stands for User Datagram Protocol. This protocol includes checksum information, which means if your packet gets mangled, there's a chance it can be detected. UDP does not do error correcting though. It often gets used for real-time communication. If you're doing a voice call and a packet gets mangled, there's no point in getting a correct version as you're already playing the audio from the next packet. And because mangled packets are problematic in most applications, your second option is TCP. This is a fully error-checked protocol. If something goes wrong, it uses the IP layer to ask the sender to repeat itself. It's also aware of packet order and will play you your data stream in the order it was sent. TCP is still pretty low level though. The communication for sending a file is rightfully different from the communication for logging into a server, and as such there are protocols that use TCP to do all those things you know and love on the internet. This top layer is called the application layer. If you ask a Python library like requests to fetch a web page, this entire stack gets used. Like I said, protocols all the way down. In the next lesson, I'll continue the networking overview and delve into IP addresses a little more. In the previous lesson, I started your network journey by revealing the layers of the Internet Protocol Suite. In this lesson, I'll be covering more details on the addressing part of IP addresses. There are actually multiple versions of the IP protocol, but for this course, I'll be sticking with the most common one, version 4. An address in IP version 4 consists of 4 numbers. Each number ranges from 0 to 255. That's an 8-bit byte. And the convention is to show them as separated by periods. You saw this in an earlier lesson where one of the IP addresses for python.org is 151.101.0.223. An IP address is hierarchical, meaning blocks of them can be owned. For example, a company could own the entire 151 parent block and then be in control over all the addresses made up of the combinations of the other 3 numbers. This isn't the case. They're typically spread out more than that, but that's the idea. An IP address only specifies a machine. In order to support multiple applications on a machine uses ports. Port numbers range from 0 to 65,535. That's 16 bits or 2 8-bit bytes. The ports are grouped into 3 chunks. The first chunk, called the well-known ports, are reserved by the Internet Assigned Numbers Authority and correspond to the services and protocols you know and love. Port 80 is the web, port 25 is mail, and the list goes on. On most operating systems, you need special permissions to use these ports. The second chunk of ports are called the registered ports, and these are semi-reserved. Semi-reserved for what, you ask? A didn't really know. In fact, before writing this slide, I had no idea these things were a thing. On most operating systems, any port of 1024 or more is yours to use and abuse. I didn't realize there was a subset I wasn't supposed to. Evidently, I've been a bad boy. If you're running the network file system protocol, for example, that's port 2049. But if you're not running it, your OS won't stop you from using that port, hence the semi in semi-reserved. And finally, the last chunk, called ephemeral ports, are a free-for-all. Ports don't only determine the service you're talking to. You also need a port on the source side of a connection. Thankfully, your OS does this for you, giving you a free port for your use when you establish a connection to the server. These free ports are always from the ephemeral group. 4 numbers from 0 to 255 gives you a total of over 4 billion combinations. You might think that's enough, but there are blocks of these numbers that are reserved for specific uses. And well, there are 8 billion of us on the planet, and although not everyone has a device yet, lots of us greedy folks have several. To get around this problem, you can proxy multiple addresses behind a router. In fact, some of those reserve blocks I was talking about are specifically for this. For example, my home internet router has a single IP address facing the world, granted to me by my hosting provider. But behind that router, I currently have 15 devices. That number seems low. I suspect something's been turned off. The 192.168 block is one of several that are reserved for private networks. This gives me loads of addresses to use on my own, all of which get mapped to the single outward-facing address my router gives me. This is why the world hasn't run out of addresses yet. Your computer might have multiple ways of talking to the internet, and as such, your operating system needs to provide a way of getting at each of these. This abstraction is known as an interface. Unless you're trying to use a specific device, you often don't have to worry about it. For example, my machine has both a network cable and Wi-Fi, but the OS decides which to use when I open a socket. These interfaces are in fact virtual and don't have to correspond to hardware. They might, like my network card, or they might be abstract like a VPN. In fact, on my Mac, there are currently 28 of these suckers. I know what maybe 4 of them are for. A little Googling tells me that Windows isn't much better in this situation. One of those 4 that I know about is the loopback interface. This one is specific for your computer talking to your computer. The neat thing about this being its own interface is that packets over this interface never make it to your network card, which makes them quite efficient. The IP address 127.0.0.1 is reserved for the loopback interface. So if some script kiddie ever asks you your IP address, tell them 127.0.0.1. There's no place like home. On most machines, the name localhost is mapped to this IP address as well. On a Unix-based system, the ifconfig command lists all of the interfaces configured. I've edited the lengthy response here and am showing only the loopback interface and EN0, which is what my machine is using for my network card. That card has an address of 192.168.123.118, which you can see in the inet line below EN0. So to revisit that diagram from the previous lesson, your machine uses a network interface, opens a destination socket. The source address of that is your local IP address and an automatically assigned ephemeral port, which might be masked behind a router, which is actually connected to the destination address and port for a specific service, which then uses a network interface on the destination machine to talk to, in this case, an encrypted web server. In the next lesson, I'll put this into practice, writing a small page fetching program and watching what it does over the network. In the previous lesson, I delved into IP addresses. In this lesson, I'll show you some actual TCP/IP traffic. To peek into what actually happens over a socket, I'm going to write a short program that fetches the home page from python.org. I'll be using the URLlib module to connect to the server and get the page. To watch the actual network traffic, I'm going to be using a tool called Wireshark. This is an open source network monitoring tool which allows you to see all the packets that happen on your machine. As that's a lot of packets, I'm going to filter the content when I capture it, and I'm going to do that using the IP address of python.org. To find the IP address of python.org, I'm going to use the NSLOOKUP utility available on most operating systems. This takes the name of a server and returns the address or addresses associated with it. You might recall in an earlier lesson, I mentioned that python.org has multiple addresses. To get around this, I'm going to use a network mask. This is a way of specifying a group of addresses. It is typically denoted using an IP address and a slash and then a bit mask. A bit mask of 16 means all of the addresses in the third and fourth blocks. Here is my simple page downloading script. It uses the URL lib module to fetch content. This is the URL of the content I want, which is the homepage of python.org. Note the commented out URL below it. I'll be talking about that later. You connect to a web page using the URL lib request class's URL open method. You can use it within a context so that the connection is automatically closed once the with block is done. Within the context argument is the connection, and here I'm calling the read method to grab everything in the page. Then finally at the bottom, I merely print out some info showing the amount of stuff retrieved and then a preview of the first 50 characters of it. Let's try this out. Running the code. And the page is just over 51K in size. Not surprising, it starts with an HTML header. My goal here is to run this exact same script while watching with Wireshark. Before doing that, though, I need a bit of information. First, I'll use nslookup to get python.org's IP address. The response here starts out by telling me where the lookup was done. The server in this case is actually my router, which is forwarding the request off to somewhere else. Then there are 4 answers, all of which start with 151.101, which is why I mentioned netmasks before. In Wireshark, I'll use a filter so that only stuff in the 151.101 range gets captured. Speaking of Wireshark, let me open it up. When you first open Wireshark, you get a list of interfaces that you can monitor. It even has a little squiggly graph here to show you where there is traffic. I want the Ethernet EN0 interface, and I want to set up a filter so that you aren't overcome with everything going on my machine. I have, let's call it, a few tabs open in my browsers. Yep, that's plural, browsers. In addition to selecting an interface, I'm setting a capture filter. That limits what Wireshark will capture from the card. This filter says I only want TCP IP traffic that is involved with the 151.101 blocks. And with that set up, I click the little fin at the top, and it starts a capture. There's nothing to see here yet because there isn't any traffic. Now, off screen, I'll run the download program. And look at all that content. I'm going to stop the capture. This is just a good habit. In theory, my filter should stop other stuff from showing up, but I've got everything I want, so why keep looking? Let me just scroll up to the top here. The protocol column here shows you what protocol the packet is using. Since the connection to python.org is encrypted, the protocol I'm interested in is TLS. Note that the first time this protocol shows up is actually the 4th chunk. TCP needs to chatter a bit to establish a connection before you can move further up the stack to the application. The client hello message here is the beginning of the TLS protocol, establishing a connection to python.org. When I click on the content, you can see all the data that went over the wire. Buried in here is the name of the server. And at the bottom, the fact that it's going to use the HTTP protocol inside of the TLS protocol. I could walk you through all of these packets, but since they're encrypted, there isn't much to see. The highlighted red item here is the close of the connection. Note how you can actually see the ports involved in this connection. 56395 is the ephemeral port on my side, while 443 is the TLS port on python.org. Encryption is useful, but gets in the way of understanding. So let's try an unencrypted connection. You might remember there was another URL in my download script. It was for a site called httpforever.com. It does not support HTTPS. This is actually handy if you happen to need a non-HTTPS connection, say when using a hotel's broken Wi-Fi. Click this to be allowed on the network to be able to get on the actual network mechanism. Off screen, I'm going to change the URL. Then I'm going to click Close Capture. And this time I'm going to need a different filter. Now I'll start the capture, run the download in the off screen, and stop the capture. The same kind of thing happens here as it did before. TCP still needs to squawk back and forth a bit, and this time instead of TLS, you see the HTTP connection. Since HTTP isn't encrypted, there's a lot more to look at here on the right-hand side. These are the headers that URLlib sent to the server. In fact, Wireshark even understands some protocols, so you can expand the part on the left, and it'll show all of this in a more readable form. These are those same headers. Let's try a little further down in the communication. This is the second chunk using the HTTP protocol, and it has all of the actual content. If I open up the text-based data, this is the HTML. All those /t's are tab characters. I guess I know which side of the tabs versus spaces argument the writer of HTTP forever falls on. Now that you've seen how all these pieces fit together, it's time to use Python's socket library to do some of this yourself.